Okay. Well, I'd like to welcome everybody to the second Mark Slade Remote Observatory virtual star party. We are hosting it tonight on a night of a club star party. So obviously there's a lot of people that are out actually looking at the stars through their telescopes, but there's a few of us who stayed home and are going to be looking at the stars virtually tonight. And our topic is going to be observing the supernova, supernova SN 2022 HRS, which was discovered on April 16th by a Japanese astronomer in the spiral galaxy NGC 4647. And it's in the constellation of Virgo. And it's a unusually bright supernova. And at peak brightness, it was probably around 12th magnitude, which is very easily within visual range of most amateur telescopes. In fact, I was able to see it myself visually with a 6-inch Newtonian reflector quite easily. And it was, of course, visible actually in larger telescopes. Other people have given me reports. 12-inch telescopes were very easy to see. So it's a bright supernova, and consequently, we have been able to get some really good spectroscopy data on it because of its brightness. And I'll share those images with you in just a moment once we get to that part. But so what we're going to do now is we're going to actually just connect to the telescopes. I'm going to go through the process. I'm going to start sharing my screen, and we're going to go through the process of connecting to the Station 2 telescope, which is a 10-inch f7.9 RC telescope. It's Station 2, we call it. And so let me go ahead and start sharing that screen right now. Hopefully it'll pull up here. There we go. So now I have already, oh, hi, John, welcome. I have already opened up some of the software to allow time to be spent a little bit more efficiently. So what I've done is I've already opened up the webcam software, which is aiming at the telescope, which is what you see on the screen here. So I'm just going to adjust the exposure setting here a bit so that you can actually see the telescope. We're going to eventually be able to see it move here in a moment once I get it on our target. But this webcam view is from a small webcam that's on top of the mobile structure, the Station 2 telescope mobile structure, which is rolled off on tracks away from the telescope. And the webcam aims down at the telescope, so it allows us to get a view. So the 10-inch telescope is what you see kind of in this just right of center. I've got a couple of yard lights near it. I was hoping they would illuminate the telescope enough that we could kind of see it. And we'll see with the moon in the sky. I think we'll be okay. We should be able to see the telescope moving. In the distance to the left is the Station 1 telescope under the dome. It's off in the distance in the tree line there. That's got a 6.5-inch APO refractor, Explorer Scientific APO refractor on a G11, Los Mandy G11 mount. And that's a 6-foot dome. And then the structure you see to the left-hand side of the screen there, that's closed up, the white curved roof structure is Station 3. And it's not in operation currently, but it has a Explorer Scientific 102 millimeter f6 or f7 refractor in there, and a nice color CMOS camera, QHY 178C, which we use for our astrophotography exercises. So what you can't see is Station 4, which is off to the left, even further to the left of Station 3, and that's got a small 80 millimeter Explorer Scientific APO refractor and on a iExos 100 mount. So that's basically MSRO in a nutshell. But we'll be using the Station 2 10-inch RC tonight for our imaging of the galaxy that contains the supernova. So what I'm going to do is let me go through the sequence now of connecting to the telescope. And I'll show you how that is done. I'm going to move things around a little bit. We're going to close out I can probably leave that screen open now. I'm going to try to move the thumbnails just a little bit here so I can see some of my icons. Okay, so to connect to the telescope, this is basically how you'd operate the telescope if you were actually observing you open up Path Hub, which is this hand paddle here. You click on Connect Telescope, which I've done, and it's going to connect to the telescope so that we can actually start communicating with it. A little hand paddle pops up in the upper left-hand corner here, which allows us, I'll slide down here, which allows us to move the telescope. And you just click OK. It tells us that our clocks are not exactly in sync, but that's okay. Okay, so we've connected to the telescope. It's live now. Now we're going to go to our software, which we're going to use to capture our images, which is MaximDL here at the top. And we're going to open up MaximDL. And in MaximDL, we have two icons we got to click on. We got to connect to the telescope and we have to connect to the camera. So to connect to the telescope, we go up to the upper left-hand corner here where there's a little picture of an observatory. We click on that and that opens up the observatory control window. And we have to connect to the telescope and the focuser. Obviously, we need to be able to focus the telescope. And so we just click connect on those two. And that's it. That's all there is on this particular screen. And now we connect on to the cameras. We click on the camera icon, which is the one that's just to the left of the observatory. And that opens up our camera control window. And we have to connect to the camera by just clicking on connect. And this is a cooled camera. We're using a QHY 174 GPS camera that Bart has put on loan to MSRO. And it is a cooled camera. So we're going to turn on the cooler. We're going to get our chip temperature down to -20 centigrade tonight. That reduces noise so that our images are a little cleaner. Okay, I'm going to minimize the screen for MaximDL. Now we're going to connect our star chart software so we can point the telescope. That's cart to seal. Let's open up cart to seal. And of course, like everything else, all the software has to be connected to the telescope. So we go into Telescope tab, drop down to Connect Telescope. And we will do that by going down to the bottom here where it says Connect. And we'll connect on that. And hopefully all three of those red bars turn green. And they do. So that tells us our scope is now live and it is tracking and it is talking to all of our software. So we are now ready to control it. So I'll go ahead and close the window. So to get to the target tonight, we use this cart to seal software, which I'm going to move into the center of the screen here. And let me just minimize MaximDL for just a moment so we can see the telescope. Because when I command the telescope to go to the target, I'd like to be able to have us watch it move here on our live view on the left. So let me just adjust the exposure a little bit longer. We'll go to 1 second. So that's going to allow us to see the telescope a little bit better. Okay, so our target is a supernova in the spiral galaxy NGC 4647. So this supernova is about 63 million light years away, which is the same distance that the host galaxy that it's in is in. And there's two basic causes of a supernova. Supernova is an immense, massive explosion of a star that increases in brightness hundreds of millions of times over its normal level of brightness, so that for a few days or weeks, it can actually put out more energy than the entire galaxy in which it was a member. And so it literally outshines the entire galaxy that it's in some cases. So the two mechanisms that cause a supernova is one is when a really, really massive star, much, much more massive than our sun, runs out of fuel. And the core of the star, which is where the energy is created, and is very, very hot, of course, and is creating this outward flow of energy. When that runs out of fuel, the core basically stops producing outward pressure, and the immense weight of the outer regions of the star begin to fall inward towards the core, and it compresses the core and heats it up to an immense temperature that's much, much higher than it was even when the core was actively producing energy. And that immense increase in pressure and energy causes a series of shock waves and explosions, which literally propagate out through the star and rip it to pieces, and in the process liberate an immense amount of energy. So that type of supernova is called a type 2. So that's a core collapse of a supermassive star. That is not the mechanism by which the supernova we're going to see tonight operates or was created. The type of supernova we're going to see tonight is a type 1A, not type 2, but type 1, type 1A, which is the result of a binary star, which one of the members is a white dwarf. A white dwarf is a very massive object. Basically, it's essentially the core that's left over when a star gently expelled its outer regions of its atmosphere into space, creating what's called a planetary nebula. And what's left over then is like a white dwarf. That's what's going to happen to our sun in about 5 or 6 billion years. But this white dwarf is closely orbiting another star, and that other star can be any kind of, it can be another white dwarf, or it could be a more likely a massive star. But they're close enough together that the white dwarf is transferring energy or matter from the larger star, and this matter builds up on the white dwarf, and the white dwarf can only get to a certain amount of mass before it collapses into an explosive event. And that particular amount of mass is when the transfer of matter from the larger star creates enough mass on the white dwarf to above that critical level, the white dwarf explodes. And that is the mechanism of the type of supernova we're going to see tonight. So to get to the galaxy, it's NGC 4647. We're going to click on that in our drop-down menu in the software, and there it is, and centered on our screen, NGC 4647. Now, to move the telescope over there, all I've got to do is click the slew button, which is this little observatory at the top here where it says slew. Now, when I click on that, if you notice the screen on your left, the live view of the telescope, you'll see the telescope should start moving. There you can see it now moving to its target. And when it gets there, on your screen on the right, on the cart to seal screen, you'll see a white box that will move onto and over our galaxy. And there it is. So according to our software now, we are on our target. Now, the thing about remote telescopes is that they're not 100% always accurate at getting to their target the first time. So we may be there, we may not. We won't be far off, but we might be far enough off that it's not on our screen. Well, let's find out. I'm hoping it's dark enough now that we will be able to see some stars here. So I'm going to go ahead and close out the screen for a moment that shows the live webcam view of the telescope. Since it's now on target, looks like it's pointing in the right part of the sky there. I'm going to minimize that. That'll just give us a little more screen real estate here. And technically, we don't really need to have cart to seal open anymore either. So I'm going to close that out. And we need to now go to our MaximDL. That's the software that we use to take pictures and to aim the telescope and to basically control everything. So it looks like I've got 2 instances of it open right now. Let's close this one since that one's not connected. No, I don't want to do that. Okay, so now here is our camera control. Looks like we're good there. I'm going to just double check something here. I thought I don't want to open. Just going to find the one that looks like the one that we're using right now. Okay, so let's go ahead. We go to on the camera control window, we go to Expose tab. And what we're going to see, the gray block in front of us is the screen that we're going to see the telescope image on. So we're going to take a picture, a single exposure, and we're going to use the open setting of our camera here. That means that there's no filter in place. The telescope has 6 filters. It has what's called the star analyzer, which is a spectroscopy grating. Then it's got a U, B, V, R, and I filters. So these are all science grade photometric filters that isolate different regions of the spectrum that are of interest for photometrists. So if you're interested in certain wavelengths, you can actually get filtered observations of these different regions of the visible spectrum. But tonight we're going to mostly be doing the V band, which is in the green. But to get to the target, I'm going to just use the open filter, which is meaning there's nothing there at all. I want to take a single exposure, single 10-second exposure. So we're starting that. And let's see if we have our galaxy on the view here, in the view. Okay, so there's something fuzzy there in the center, isn't there? So that could be it. I'm going to adjust the setting. It's still a little bit light out there. And that's why the picture looks rather grainy, is because it is still a little bit light. Twilight is still going strong out there. But I'm going to just adjust the display settings on the screen here a little bit by bringing up the screen stretch window, and we can adjust this and we can kind of see that there is something fuzzy there. Now, if I go to full size here, 100% view, we notice something. The stars are a little bit out of focus. And that's because the setting for focus right now, I believe, is for the photometry filter, the V band. So I'm going to do that. I'm going to go now and I'm going to go back to the filter wheel. I'm going to put the V band filter in, which is like essentially green. And that's typically the standard wavelength that we measure brightnesses of these objects in. I'm going to take another 10-second exposure. And we should see that it's a little bit better focus. And I do believe we are on target. I think this is the galaxy here. So we may not have to worry about plate solving here tonight. Yes, yeah, we're on target. No doubt about it. We are still a little bit out of focus. So what I'm going to do now is I'm going to show you how we focus this. But this bright fuzzy object right here is the elliptical galaxy M60. That's not our target. Our target is this fuzzy blob down here. That's the galaxy NGC 4647. And this object right here, which is out of focus right now, which looks like a fuzzy star, is actually our supernova. So let's get this thing focused. So what I'm going to do is I'm going to go to continuous mode. And I'm going to start 10-second exposures. And now it's just going to take one 10-second exposure after another. And I'm going to go over here now to the observatory control window. And I'm just going to move the focus in and out, just randomly. I'm going to go in 50 increments. And we're just going to watch and see if the stars look like they're focused better. If we went the right way. I think we went the right way. So I'm going to go 50 more. So I'm just clicking the move in button under observatory window. This is our focus. So we're just going to bring our focus in. Yeah, it looks a little bit better, doesn't it? I'm going to go 50 and more. All right, it's getting better still. So you can kind of see the galaxy is looking like a little fuzzy blob, but they're just to the lower left. So this is our supernova right here. I don't know if I'm drawing a little box around it right now. If you can see that on your screen, I'll move my cursor around it too. That star, quote unquote, using air parentheses, is not a normal star. That is a massive explosion that's occurring in this galaxy right down here to the lower left. These other stars that you see in the view are just that. They're normal stars in our galaxy that are in the foreground. I'm going to go in 50 more, one more time. And I think that should get us pretty close to focused. Then I'm going to get it set up for a 60-second exposure now. So we are good. That's good enough for photometry right now. Okay, so that looks pretty good. So now what we're going to do, let me go ahead and stop the exposure here. We are going to do real science. So what I have in place is we're looking through the photometric V band filter right now, which is essentially, it's in the green region of the spectrum. But it lets a region of the electromagnetic spectrum through that is the most commonly used when you are looking at the brightnesses of objects professionally, when you want to create light curves and things like that. Astronomers like to use what's called the V band filter. If you've only got one filter, that's the one you want to use. So we're going to use that. So what I'm going to do now is I'm going to go ahead and close out that window for a moment, and we're going to set up a series of exposures. Now, this is how we do real science. So we got our target on the screen. I'm going to go down to the autosave button. Autosave feature allows us to create a menu of exposures that the computer and the telescope will now do automatically for us. And we're going to name it Supernova 2022 HRS under autosave file name, which that's already set. All these columns you see 1 through 6 are all of our different filters. If I click on 1 or 2, it gives us, it tells the computer that we want to go ahead and use that filter for our observation. So we're going to use filter 2, and we're going to set it for 60-second exposures. We're going to take 10 exposures, and we are going to go ahead and say apply. And then we're going to set the save image path. So we got to tell it where we want to save it. So we're going to save it under the directory 2022 HRS. We're going to make a folder for tonight, which we're going to call 2022. Oops, I got to type better. 2022-06-05. That's universal time. We're on June 5th right now. Okay, and then there's our folder, and now we're going to create a subdirectory under that, which says photometry, so that way we know that our photometric data will be in that particular category. And then we hit OK, and now we're ready to go. So hit OK here, and now we're going to start our exposure. So now what we're doing is the telescope is now exposing a 60-second exposure. Hopefully it's dark enough out there now that it won't saturate our image, but we'll find out here in just a moment. Now, I think when we run out of time on this meeting, I think at 9:40, I think we can just all log back in a second time. I'm not sure how that works. This is part of the learning curve for me here. If we can't log back in, then that will be it for the meeting. And we got through at least this part. We got to see how to take photometry. If we can log back in, we'll continue, and we'll do a spectroscopic observation after this. So we'll do, I'm not going to do the full 10 because it may be that we'll run out of time. Well, actually we will. We'll just kind of watch what happens here. And this would be a good time now to entertain any questions if anybody has some while we're watching the data come in. So I'll close my mouth for a few minutes and open the floor up to anybody else who wants to. Oh, that's out of focus. What happened there? That's kind of, I thought we focused it. Yeah, that's way out of focus. So that's our first 60-second exposure. So let me just stop this. Let me go back to continuous here. And let me go back to 10 seconds. And let me just tweak the focus on this again for us. I'm not sure why that was looked like it was focused for us a minute ago. All right, let's go to the focus tab. And I'm going to move out this time. Maybe I moved in too far. So does anybody have any questions so far?
I think you might have not looked at the last image after the last time you pushed.
Yeah, maybe that may have been it. I'm gonna go out again a little bit more. I think that's a little bit better focus there. I'm going to let it go one more. Sometimes we're like a delayed by one, and you get tricked into thinking that it's, I think that's probably good enough for our photometry. We don't need to nail the focus perfectly. So that's good. Okay. So I think we're better in focus now. So let me go ahead and let's bring up our camera control window again. Let's stop. Let's go back to auto save. Let's try another 60-second exposure. Just double check everything here. Looks good. Okay, and all right, let's try it again here. Hopefully we get a little better focus this time. The nice thing about photometry is that it doesn't have to be perfect focus, because really all you're looking at is the amount of light that falls into a certain defined area, a circle around the star, and the software sums it all up. So it doesn't have to be exactly focused. So if you're taking, a really good, if you want to get a nice pretty picture, then yes, absolutely spend time focusing. But if you're going to be doing photometry, you don't actually have to be in perfect focus. Sometimes some folks feel like you actually should be a little bit out of focus because that helps reduce some of the variability due to twinkling and things like that. So I've been observing this since about the 18th of April, and we have data on almost every clear night. So we're going to be constructing a light curve, actually, that will help us, that we will be able to actually present at one of our meetings. So it looks like we got 10 minutes. All right, so I'm going to go ahead and bring this here, and I'm just adjusting the screen stretch a little bit so we can see the galaxy. Again, now this is a V-band image, so this is not the full amount of light getting to, we're cutting out a lot of the light to that gets into the telescope by putting a filter in place. If the filter was not in view, was not in place, the stars would be bright, you'd see more stars and you'd see the galaxy easier. But we're doing real science right now. So we're getting actually V-band photometry data on the supernova. Again, this is the supernova right here. I'll put a little square around it. That's our target right there. And we're still a little bit out of focus, I can tell that. But again, that won't matter. Even though these images look kind of noisy, when you stack them, they turn out to be actually very nice. I'm going to bring up, let me show you what this recent image that I took of this particular object while we're waiting for the data comes in, because it's kind of boring just watching the data come in some cases. So let me show you some images here. Let me just slide this around a little bit here. And let's say, sharing my screen right now. Okay, it's here. All right, I actually have those on my other. So I'm going to do now, I'm going to go back to the screen. Let's see, this is it here. Okay, yeah. Can you all see this? Can you guys see this graph of the red line that looks like a bunch of jagged peaks? Because I'm not sure if this screen is showing you or not.
No.
No, it doesn't look like it.
I'm sorry, say it again, Bart.
Doesn't look like we're seeing that.
Okay, so I guess I have to share. All right, let me go ahead. I'm going to go to my control here and new share, and there we go. Okay, now you should be able to see it.
There we go. Yes.
Okay, excellent. So this is a spectrum of the supernova that we're looking at right now. That was created back at the end of April, data that I used in April, and it shows various emission and absorption lines in the spectrum. And interestingly, you're able to tell a type 1a supernova fairly easily by looking at the spectrum because of a feature known as the silicon absorption band, which is this deep, I don't know if it'll, if you can see my mouse, this deep
Yes.
valley at about 6,200 angstroms. It's about the darkest feature on the spectrum if you look down, at the synthesized spectrum on the bottom. That's due to silicon, which is created during the supernova explosion, actually. And it's characteristic of type 1A supernovas. And so it showed up pretty clearly on our data. So this spectrum has been calibrated for wavelength, obviously, because you need to be able to know what wavelength these features are at. But it was also calibrated for instrument response, meaning that our camera has basically a non-linear sensitivity to various regions of the spectrum. So the actual object might be emitting very strongly in, like, let's say the blue region of the spectrum. But because our camera is not very sensitive to the blue region of the spectrum, our camera would record that part of the spectrum as being dimmer than it should be if you don't calibrate the data for instrument response. So there's a process that you go through where you calibrate your camera and you characterize its sensitivity at all the different wavelengths across the visible spectrum. And then you apply that particular pattern to the raw data, and then you get what's called an instrument response calibrated spectrum. And that's what this is. So this is closer to the reality of what the spectrum looks like in this particular object. Now, it's not perfect. There's some errors because, you know, there's atmospheric absorption features probably in there as well, and I haven't canceled those out. But this still nonetheless agrees pretty well with a lot of the spectrums that I've seen online of this particular object. So I thought I was very happy about that. Now, let me see if there is another, let me close this out. Let me go to a new share again. I'm getting the hang of this here. Let's go to new share. Go back to, okay. Do y'all see the data coming in again? This is the live view now.
Yes.
Okay, so I'm back on that. Now, let's take a look at the telescope again. We'll go to live view of the telescope here. We're not gonna have time to do the spectroscopy, but we can finish up with one more view of the telescope here. So I'll do that. Here's the view of the telescope. So that doesn't look too good. We can't even see the telescope. So let's go to a little bit longer exposure time here. We'll go to 4 seconds to see what that looks like here. So it's kind of hard to see the telescope because there's so much stray light. And it looks really, really bad. All that stray light looks like it would be a horrible observing location, but it really isn't. When you go out there and you're actually walking around the yard, it's pretty dark back there. Even though there's a lot of lights, these lights really don't mess with the telescope. Now, I don't normally observe with the ground lights, those 4 yard lights that are at the base. I put those out there hoping they would allow us to see the telescope a little bit better just for this presentation. They're normally not there, but they don't seem to be really doing a whole lot helping us with seeing the telescopes. I probably won't use those again. But anyway, okay, so close that out. We have, let's see here. We're on image 9 of 10. So we got 2 more images, and then we've got our V-band data in, and we'll be able to actually add a point to our light curve that we can put a little arrow on that says this point was obtained during our MSRO star party, because this data will be used in constructing our light curve when I do that. Okay. So do y'all want to try linking up again for another 30 minutes or so using the same link? I'm not sure if that will work. Jerry said he thought it would.
Yes, I think you need to restart your host meeting.
Okay.
And we can then connect up using the same link.
So I just restart a new meeting basically, right? And then do I send you? I think you can use the same link, can't you?
If you use the same, yeah, if you use the same, like your personal meeting
Yes.
ID, if you use that, then the same link will work.
Okay. I'm not 100% sure. that I'm going to be able to figure it out, but I'm going to give it a try. If not, if I can't get you, you know, if you don't see it, come back, then we'll just call it a night for this particular, and we'll maybe do spectroscopy next time. We'll do another one in another week or so, and we'll concentrate just on spectroscopy. Okay.
Okay.
So thank you everybody for joining, and hope you all have a nice evening. If we don't link up again, but if we do, I'll see you guys shortly for some spectroscopic attempt.
Thank you.
Okay.
Okay.
All right. Bye-bye.
Bye.